Okay, we continue. Do you have questions concerning this definition of luminosity?
Yes, Professor. If experiment have 5 sigma, does it luminosity also large?
Luminosity can be anything, but we actually would like to exclude it from the results, final results of the experiment, because again, let me say that luminosity, well, of course, the more luminosity we have, probably the easier way we can arrange our experiment. So luminosity is still an important quantity. It shows how well your machine is. But at the end of the day, what we would like to do, we would like to study the microscopic loss. We would like to understand the microscopic loss which drives the scattering, not the machine which produces the particles. And that's why at the end of the day, we have to define the quantity which somehow excludes the effect of the machine itself. And this quantity is a differential cross-section.
Okay, I see.
And this is what I'm going to define now. So, well, I have not yet finished with the luminosity, because we have computed this quantity, as you see here, or defined this quantity in the laboratory frame. So in the frame where particles of the second beam are actually at rest and represent the target. And we therefore need somehow to find these quantities like V1, ρ1, and ρ2 in the laboratory frame, where the original quantities ρ1 and ρ2 and V1 of the particles in the beam, in the original beams. So let's start from velocity V1 in the laboratory frame. This can be found by considering the following Lorentz invariant quantity. So as you know, if you have two vectors, 4 vectors k1 and k2, then the scalar product k1 to k2 is a Lorentz invariant quantity. So this is Lorentz invariant. The product of two vectors is Lorentz invariant quantity. And if you specify this product to the laboratory frame, what you get? You get K1 0, K2 0, minus K1, K2. But in the laboratory frame, you get actually this to be 0, because K2 is 0. Particles in the second beam are at rest in this frame. And so you just get the product of energies. And the energy of particle in the laboratory frame, then just the mass divided by square root. No, if we write actually this by taking account the speed of light, then this should be m1c divided by 1 minus v1 laboratory squared divided by c squared. This is K01, right? Multiplied by K02, but this energy of particles at rest, so it's simply M2C. And this then means that what I have is M1, M2 divided by square root 1 minus V1 laboratory squared over C squared multiplied by C squared. And this is quantity which is Lorentz invariant. So on the left-hand side, and I can use this formula in order to express V1 in the laboratory frame. And so solving this equation, you can find from here V1 in the laboratory frame as a C square root K1 multiplied by K2 squared minus M1 squared M2 squared divided by K1 K2. So this is how this quantity now is expressed via the momenta of the particles in the first and the second beam. The second thing is the transformation law for the particle density. So this quantity, particle density, also depends on the Lorentz frame. And you can find it in the following way. So the quantity, which is Lorentz invariant, is a number of particles in the volume dV. So in other words, number of particles is density of particles multiplied by the element of a volume by dV. And so this is dN, the number of particles in a volume dV. This is Lorentz invariant quantity. You know that the volume is not Lorentz invariant because of the Lorentz contraction in the direction of motion. The volume V or dV, its differential, is not Lorentz invariant quantity, but rho is also not Lorentz invariant, but the product of rho with dV is Lorentz invariant. So if you want to find the density in the moving frame, density of particles in the moving frame, and the element of volume dV, then in the stationary frame, it would be, say, rho 0 dV 0, and this, let's say, this is the density of particles, say, at rest in the stationary system. dV0 is the volume in the stationary system. And now taking into account the Lorentz contraction of the volume in the moving system, you find from here that rho V is simply given by rho 0. And then this relativistic prefactor, which describes contraction of the volume, contraction of the length in the direction of motion. And so if you wish, you can rewrite it as a rho 0 multiplied by K0 divided by mass, because I can multiply it by M, no, maybe also C squared. So let's not think much about this. So multiply and divide by mass, then this quantity here, if I multiply by C squared, then it becomes just energy, K0, and then I divide it by MC squared, and then this is the density of particles in the moving frame. Now, we have introduced a number of different densities. I introduced density in the rest frame, density of particles in the moving frame, where particles move with velocity v, and the density of particles in the laboratory frame. And we need to express the luminosity actually via two quantities, rho v1, where density is considered as a density in the original beam, where particles move with velocity v1, and density of particles rho v2, which is the density of particles in the second beam, beam of particles moving with velocity v2. Now, for the moment, what we have is the density of particles from the second beam in the laboratory frame. That's the same as rho 02, because in the laboratory frame, particles are at rest. Yes, so particles are at rest. And so if you now consider this quantity which enters the luminosity, the product of these two densities in the laboratory frame, then we can write this in the following way. So we can write rho 1 divided by square root 1 minus V1 laboratory squared over 2. This would be rho 1 laboratory. ρ1 laboratory, where ρ01 is the density of the first particles at rest divided by the relativistic prefactor, taking into account the fact that in the laboratory frame, particles from the first beam have velocity v1 laboratory, and multiply by ρ2 laboratory. This then can be written in the following way. ρ2 laboratory, let's see. We have this formula here, which allows us actually to rewrite everything via ρ0, 1 and ρ02, and this will read in the following way. So this will be, let's see how we write it. It's K1 multiplied by K2 this is the way I express this square root, 1 minus v1 squared, this one. And I need to divide it by m1, m2. Then this is what replaces for me the square root. ρ01 I left without change, and ρ2 laboratory, I know that in this frame, my particles too are at rest, so it's the same as this quantity here. And so this means that I have written down the product of the densities in the laboratory frame with the product of densities where particles from the first beam and from the second beam are at rest. And this I can manipulate further in the following way. So this is K1, K2. I divide by M1, M2, and then I multiply it by M1, M2, divided by K01, K02, multiplied with ρ1v, ρ2v. And here I actually use this formula here. If you forget for a second about the speed of light, I don't care too much here about the factor of c, because at the end of the day, we can put c to be equals to 1. So this is not so important for us. But what is important then from this formula, I see that ρ0 is ρv divided by k0, divided by the energy in the frame where particles move with velocity v. And so what I'm doing here, I'm using this formula, and I'm replacing, yes, and I need also to take into account the mass. So mass goes where the mass goes here. Mass goes here. So I'm using this formula and replace ρ01 and ρ02 by these expressions. And that gives me exactly what I want. So these two factors canceled, and I get that the result is K1 multiplied by K2, K01, K02, ρ1v, ρ2v. So I expressed the product of densities in the laboratory frame via product of densities of particles in the frames where particles are moving with velocities v1 and v2. So densities of particles in the original beams. Okay. That essentially means that I can now write luminosity in the following way. So V1 laboratory, remember this is V1 laboratory, ρ1 laboratory, ρ2 laboratory, multiplied by V. That formula becomes V1 laboratory is going where this formula here will be replaced by this formula here. So this is K1, K2 squared minus M1 squared, M2 squared, divided by K01, K02. And this is multiplied now by the product of densities in the laboratory frame, which we have found here. And this gives us, let's see what it gives us. Right. So K1, K2, which was in the denominator, cancels out with K1, K2, which will be in the numerator. K01, K02, I have already written down. And so what is left over is ρ1 V1, ρ2 V2, and the factor of volume V. So this is luminosity as written down via the quantities related to the first and the second beam. Now you can see from this expression that L dt, luminosity multiplied by element dt, is Lorentz invariant quantity because V dt is a Lorentz invariant quantity. So V will be multiplied by dt will be Lorentz invariant quantity. And the ratio rho V divided by K0 is also the Lorentz invariant quantity. Lorentz invariant, because the change of the density by changing the Lorentz frame will be compensated by changing the energy factor K0 when a Lorentz frame is changed. So this quantity is also Lorentz invariant. So this ratios K0 to velocities, this quantity is a Lorentz invariant. Typically, the normalization which people undertake in order to compute the scattering cross-section is that they assume normalization ρ1 V, ρ1 V1 equals to ρ2 V2, where the accelerator produces one particle per volume V. And so this is typically what is taken as a particle densities in the beam, in the first and the second beam. And in this case, this Lorentz invariant luminosity, or luminosity multiplied by dt, the Lorentz invariant quantity, is now taking the form m1 squared, m2 squared, divided by K01, K02, C divided by V. C divided by V. This quantity has the right physical dimension. If you substitute here the dimensions of all the quantities you have on the right-hand side, you will find out, you can check me, that luminosity is 1 divided by T time, it has dimension of time, multiplied by L squared. So that's exactly what is expected. So luminosity is a number of particles per unit time per unit cross-section area. So luminosity is this quantity, which has this physical dimension. And finally, we can get the formula for the cross-section. So what we do, we take now, say, cross-section 2 to the n. So two beams, two particles in the two beams collide into, say, in general, n particles. And then the sigma differential cross-section is defined, as I said at the beginning. We divide differential cross-section by luminosity. And differential cross-section is coming back, is given by this quantity here. And this is d ellipse. So d ellipse is related to the measure related to the outgoing particles. So I leave it for the moment as d ellipse. And so we will have a scattering amplitude. And then if I substitute everything in this formula, then I will get this sigma is the following quantity: AFI modulus squared divided by what? 4c squared. If you follow the coefficients accurately, then this is what it is: K1, K2 squared minus M1 squared, M2 squared, and then D ellipse, and then the ellipse. Okay. Now, if you look at this quantity, then you see that it involves only Lorentz invariant objects. So amplitude is Lorentz invariant. The square root in the denominator is Lorentz invariant, and the ellipse is also Lorentz invariant. So this means that due to this Lorentz invariant nature, the cross section can be computed in any convenient Lorentz frame. For instance, in the center of mass frame, where the computations become very simple. The second thing is that you may consider the scattering of unpolarized particles, for instance, electrons or photons, or scattering of different polarized particles. So if you are not considering, if you consider just scattering of unpolarized particles, then to get the corresponding cross section, you have to sum up this amplitude AFI squared and correspondingly the cross section over polarizations of outgoing particles and average over polarizations of incoming particles. And this average over polarization of incoming particles is simply that you take the arithmetic mean. So you sum up, so typically you have two polarizations, say for a photon, linearly polarized, you have two possible polarizations, and you sum the corresponding amplitudes for different polarizations, and then you divide it by 2. So you take an arithmetic mean, and when you register your outgoing particles, you need to sum up over all possible polarizations. So this means that in the case of having unpolarized particles, both in the initial and the final state, total quantity to compute would be something like 1/2 due to this averaging sum over polarizations of incoming and outgoing particles, AFI squared. If you, for some reason, your accelerator produced polarized particles with a certain density, then you need to use something which is called density matrix for particles with different polarizations. But let's not go to these issues that provides technical complications. In any case, if you're just talking about unpolarized particles, then this is a way to compute the corresponding contribution to the differential cross-section. Okay, and what else should we set here? Now, what we can do with this formula in order to apply it later for a concrete processes, for instance, in quantum electrodynamics, we can just go on with this formula and compute, say, the simplest cross-section where two particles go to two particles. We have everything prepared. We have everything at our disposal, all the tools. because we know what this sigma is now. And we also know what is the ellipse, because we have already computed it for the case of the Lorentz invariant phase space associated to two outgoing particles. So the simplest scattering event is 2 to 2. This is one of the most probabilistic scattering experiments, 2 to 2 scattering. To compute the corresponding cross-section, we assume that incoming and outgoing particles have momenta k1, k2, so incoming, and k3, k4, outgoing. Since the cross-section is Lorentz invariant, we can compute it in any Lorentz frame. And as we discussed, the most convenient is the center of mass frame. So in this frame, K initial, K in, is equal to 0. And what is K in? K in is K1 plus K2, right? K1 plus K2, K in, and it's equal to 0. So it makes sense then to define, to take one of these momenta as the reference momentum with respect to which we will be writing everything, and then K1 is minus K2. And let's denote this as, simply as K. Let it be K. Yeah, I don't know how to. Yeah, maybe this is a way to write it. Then, since we have the conservation law that initial momentum is equal to the final momentum, we have K final as K3 plus K4. And this is then also equal to 0 because momentum is conserved. And so we have K3 is equal to minus K4 in this frame. Now, to use our formula for the differential cross-section, what we have to do is to evaluate K1, K2 minus M1 squared, M2 squared in the center of mass frame. And in this center of mass frame, we have, so first of all, scalar product. So this is K1, 0, K2, 0, minus Ki, I raise an index, then I get K1, K2, like this, squared. Squared. Sorry, this is not what I wanted to write. Let me see. Right. So here this is incorrect what I'm writing. Let me write it more accurately. So I get K1, K2 plus. Let's do it slowly. Plus Ki 1, K2 I2. This raising up index up gives me minus sign, but the fact that K2 is equal to minus K1, that means minus K, I can write this expression as K10, K02 minus K squared minus M1 squared, M2 squared, right? So as way around, minus with minus, it just gives me plus. That's why I get this plus. for this expression. Now we can open this square and get the following expression. So this is squared actually here. Yeah, remember? Yeah, this is square. Open it up. What we will get? We get k01 squared, k02 squared, plus 2k squared, k10, k20 plus k squared squared minus m1 squared, m2 squared. And now we have to remember that k01 squared is nothing else as due to the dispersion relation is k squared plus m squared. Yes, because k1 is k, and this is m1 squared. Yeah, I don't need square root here actually, because I'm writing this for the square of k01. So analogous k02 is minus k squared, so the same as k squared plus m2 squared. And then we take this square, substitute into this formula here, and get the following answer. So if you allow me to continue this expression and substitute, so I get k squared plus m1 squared, k squared plus m2 squared, plus 2k squared k01 k02 minus m1 squared m2 squared. So if you open the brackets, let's see what we get. Let's see what we get. One thing which I also missed is this k squared squared. It's coming from here, it's this term here. So if I open the brackets, I will get twice k squared squared plus m1 squared plus m2 squared k squared, and then product of masses will cancel with this term here. And so on the top there will be 2 k squared k01 k02, and so this allows me to take out from this expression k squared. So I will be left over with k squared twice plus m1 squared plus m2 squared plus twice k01 k02. This is what I will get. And miraculously, you see that this nicely combines again by using this formula. So k squared plus m1 squared gives k01 squared. So you'll get k01 squared, right? The second mass with k squared gives k02 squared, very nicely, plus 2k01 k02. And of course, you see binomial here. So things combine and you get k01 plus k02 squared. Okay, so this is, we are computing this quantity here in a particular frame. I recall that this is a center of mass frame of incoming particles, and we see that this is an expression we get. And so now, if we take our differential cross-section and substitute d ellipse, which we have found before, for two-particle Lorentz invariant phase space, then d sigma over d omega, so distribution differential cross-section per unit solid angle in a center of mass frame, computed in a center of mass frame, takes the following form. So amplitude Fi squared divided by 64 pi squared c in the power 4, k0 squared, so energy of the incoming particles, then this vector k star, and not the vector, this value k star, which comes from solving the equation I showed you before, and this will be divided by modulus of this vector k, which I have just introduced. So this is how the answer would look like. K0 K0 is K10 plus K20. And this means that I can introduce energy in the center of mass frame, and this is energy is just essentially this is just K0. This is just K0. Any questions here? Do you understand how I computed this quantity? You see, in order to compute the d sigma, I have to take a square root. So taking square root of what I have found. So from here, it follows that taking square root of K1, K2 squared minus M1 squared, M2 squared, I will simply get modulus of K multiplied by K10 plus K20. And this is simply the energy K0 of total energy of incoming particles. You see it, so this vector of here, another vector of here, it's coming from this formula. And K0 with K star comes from the formula for d-ellipse. That explains the appearance of all these vectors here. Now, a particularly simple formula arises for the case when the masses of incoming particles are equal. Because in this case, if you go to our expression for K star, let's look again at this expression for K star. Yeah, here it is. So you see, if masses of all masses are equal, then what do we have? Then this term disappears. This term disappears. That becomes 0. So K0 gets out and cancels the K0 in front. And 4m3 is equal to m4 is equal simply to m. And this formula turns into or gets into 1 divided by 2 square root K0 squared, energy of incoming particles squared, minus 4m squared, right? This is m3 plus m. 4 is k squared. And now, if you remember what is K0 squared, so K0 squared, let me see. If masses are equal, then K10 is equal to K20 equals to square root of K squared plus M squared, right? And if you now compute K0 squared, then what is this? K10 squared plus K20 squared plus twice K01. K02, but they are equal. Therefore, you get K10 squared. So they are all equal. So you get 4 times K01 squared, which means you get 4 times K squared plus M squared. And therefore, if you plug this expression into this formula, masses completely cancel out. And you simply get that K star is given by the modulus of K. K star is given simply by the modulus of K. That's the conclusion. So if all the masses of particles do not change in the process of scattering, then the answer we get is very simple. We just say that in this situation, K star is equal to modulus of K, and so these two terms then cancel out. And in the case of all masses to be equal, differential cross section, d sigma over d omega, in the center, computed in the center of mass frame, takes the following form: scattering amplitude squared divided by 64 pi squared C4, K0 squared, which is the same as amplitude Fi squared divided by 64 pi squared C4, and K0 squared is simply energy of the incoming particles squared in the center of mass. That's the answer for this differential cross section. D sigma over d omega. In particular, if you remember if you recall our previous lecture, then in that lecture we computed the scattering amplitude for the phi-4 theory at leading order in perturbation theory. So phi-4, this was a complex scalar field, and we have found out the scattering amplitude for two particles to two particles, either particle particle to particle particle, or particle antiparticle to particle antiparticle, or antiparticle antiparticle to antiparticle antiparticle. The result for this amplitude at leading order of perturbation theory was g c squared divided by 3 factorial. So it was just a number proportional to the coupling constant. And so if you substitute it into this formula, then you get the differential cross section or distribution of d sigma over d omega. Simply, I restore now also all physical units. So the powers of h bar, g squared, and then some numerical prefactors, pi squared, and the energy of incoming particles in the center of mass. And so would it be the theory of a self-interacting complex scalar field? Then this is a prediction for experimentalists to find this number, at least at the leading order of perturbation theory. The main contribution should be provided, and this is how this differential cross-section should look like. This is what will be registered by the devices if two beams of our particles or antiparticles corresponding to the complex scalar field will be sent to the interaction region. Okay, so this is what concerns today with the notion of the differential cross section and its in a way practical construction starting from the transition probability differential transition probability, luminosity, and the ratio of differential probability to the luminosity gives us this notion of differential cross-section in quantum field theory. Now, let me also add to this something about the kinematic invariance for 2-to-2 scattering, since this scattering process, as we say, is a main process which often happens, so 2-to-2. If you consider such a scattering process where in the initial state there are two particles, say with momenta p1 and p2, so momenta of incoming particles, and in the initial we have momenta p3 and p4, then the conservation law is telling us that p1 plus p2 is equal to p3 plus p4, right? That's what conservation law is telling us. Now, the scattering amplitude is a Lorentz invariant quantity. This AFI, which enters the answer for the differential cross-section, is Lorentz invariant. Which means that this amplitude can be written only where Lorentz invariance you may construct from this momenta p1, p2, p3, p4, subject to the conservation law. Subject to the conservation law we have. Now, this means that in the game there are only three vectors due to the conservation law. For instance, we can exclude p4. And so we have three vectors, p1, p2, p3, from which we can construct 6 Lorentz invariants. 6 Lorentz invariant quantities. Quantities we can construct. What are these quantities? I think you know them very well. So this is pi squared we can take for I being 1, 2, 3. So square of the vector is a Lorentz invariant quantity. Then we take scalar products, p1, p2, say p1, p3, and p2, p3. So 6 Lorentz invariant quantities. On the other hand, the squares of momenta, so p1 squared, p2 squared, p2, 3 squared, these are equal to the corresponding masses squared. So, for instance, the mass shell condition, because we are talking about momenta of asymptotic particles, then there are these relations which tell us that actually these Lorentz invariants are just masses of the particles. So these squares can be just replaced by masses. So this means that we have to concentrate on the remaining 3 invariants. And also we have the following relation. So because we can express P4 as P1 plus P2 minus P3, and then take a square of this equation, and P4 squared is equal to M4 squared, then this becomes P1 plus P2 minus P3 squared, which means that essentially this gives one relation between these 3 quantities. When I will be taking squares, again, P1 squared plus P2 squared plus P3 squared, this can be replaced via masses, and then I will get products, I will get scalar products of these vectors, and then this relation here will impose one condition on 3 Lorentz invariant scalar products. So at the end of the day, the amplitude 2 to 2 will be described by means of 2 Lorentz invariants. And in practice, it is convenient to introduce the following Lorentz invariant quantities, which people use to describe the amplitudes. They are called Mandelstam variables. Mandelstam variables introduced by Mandelstam. This is C, T, and U, introduces three variables corresponding to three reaction channels, S, T, and U. S invariant, Lorentz invariant, is P1 plus P2 squared, which is of course the same as P3 plus P4 squared due to the conservation law. T is introduced as P1 minus P3 squared, which is of course the same due to the conservation law as P2 minus P4 squared. And finally, one introduces U invariant, which is P1 minus P4 squared. And this is the same as P2 minus P3 squared. But as we said, in reality, there are only two independent Lorentz invariants. And this means that this STU must be related by one relation. This relation you can easily derive from this equations, namely S plus T plus U. If you sum all these three invariants, you will get H, where H is a combination of masses. It's just sum of squares of the masses. So this is a way you can parameterize the amplitude, and typically people take to parameterize the scattering amplitude by using invariants S and T. But in many cases, it's possible to yes, you can play with this relation, and you can express it either with S and U or T and U, depending on what is more convenient for your purposes. In any case, for a scattering 2 to 2, the amplitude must depend on two independent Lorentz invariant variables, and Mandelstam variables are useful to use in this respect. Okay, any questions?
Professor, the last expression we found of the cross section, I wonder this dependence of the inverse, the square of the energy of the in the rest. We have some interpretation for this. Why we have physically why this behavior with the energy.
Yes, so the behavior is that if you get more energy to the incoming particles, then the sigma over the omega appears to decrease. But this is in a way understandable because because you don't give enough time for particles in a way to interact. You should give them time, right? You should give them time to interact.
Thank you. Yeah.
I mean, this is how it looks like in the center of mass frame. So although d sigma over d omega is independent on the Lorentz frame, does not matter in which Lorentz frame you compute it, d sigma. The result we have written down here explicitly, we written it via the quantity which is related to the center of mass frame of the incoming particles.
Okay.
Right.
I have a question about this. If we have 2 to 2 scattering with 4 massless particles, we will get the same result here.
Which scattering 2 to
2 to 2, but massless.
Yeah, so for massless particles, of course, you need to take into account certain modifications, because we were relying here on the fact that our particles are massive. So I think at a certain point, yes, I will, well, actually soon I will show you a computation of the actual process in quantum electrodynamics, which is called Compton scattering, where you will have a scattering process of electrons with photons, and photons are massless. So in this case, massless particles will be involved. In principle, all the formulas remain the same. You don't have much modifications. The formula for d sigma remains to be the same. Yeah, you just have to be a little bit accurate and take into account, say, that the mass of photons is 0. But the main formula remains to be the same. There's no changes indeed. I think it will be the same, yeah. The only point is that center of mass becomes a little bit problematic, because photons are moving with the speed of light. So in this case, I think you can, but if you, of course, consider scattering, say, of photons, photons with photons cannot scatter. I told you about this already, right? We discussed it. Scattering light on light is an effect of the higher order of perturbation theory. It comes through creation of electron-positron pair, so it's not obvious I mean, it is not a direct effect. It comes only through creation of electron-positron pair. So photons on photons you cannot scatter directly. But you can scatter photons with electrons, which is Compton effect. And in this case, of course, our considerations remain to be true. All what you need to take as a target are electrons, because electrons are massive, and you can find the Lorentz frame where they play the role of the target. And then our considerations remain to be true. Modulus the fact that photons, which are coming on this target, move with the speed of light. And then you know that speed of light is a quantity which is the one and the same in a Lorentz frame, and then you have just to take into account this fact. Otherwise, there will be no further modifications of our discussion. Now, in the remaining time, I would like now to come to the important subject, finally, of our discussion, namely S matrix of quantum electrodynamics. Now we are talking really about physical theory, S matrix of quantum electrodynamics, S matrix of QED. And in order to describe this S matrix and the way how it can be computed in perturbation theory, we need first to specify, to write down the Lagrangian of quantum electrodynamics, so the action, and then also to, how to say, to give all essential ingredients which are needed for, say, constructing the scattering amplitude and the Lorentz invariant cross-section for the processes of quantum electrodynamics. And in this respect, it is reasonable to start from the action of quantum electrodynamics. So let me write down this action. I think both the components of this action we have already discussed. So the action of quantum electrodynamics essentially consists of 3 terms. The first term involves Dirac fermions, which describe electrons and positrons. So I'm writing the Dirac action. And I'm writing this action of quantum electrodynamics with all the constants. So I'm not putting speed of light and h bar to 1, because I want to show you how it looks like in full reality. So how this looks like the action for our physical theory describing light and matter. Then there is a piece which describes the action for electromagnetic field. Right, so Dirac action we know, electromagnetic field, the action we know, that's just Maxwell action. And on the top of that, we add up interaction term, which describes interaction of electromagnetic current, the current produced by fermions, by the Dirac field, psi bar gamma mu psi, that's a conserved current, multiplied with A mu, where A mu is electromagnetic potential. So this essentially, this is a term which describes interaction of photons with electrons and positrons. E is an electric charge here. And very often it is convenient, starting from the section, to make the following rescalings of the fields. So psi is rescaled by psi divided by square root of h bar c, and electric field is rescaled by A mu divided also by square root of h bar c. Square root of h bar c has a dimension of electric charge. Now, in this, upon performing this rescaling, then the physical dimension of a new fermion is 1 divided by length in the power 3 over 2. And for vector potential, the dimension is 1 over length. 1 over length. So after doing this rescaling, the action of quantum electrodynamics takes the following form in terms of new fields, rescaled fields. H bar gets out in front of the whole action. Then there is an integral d for x psi bar I gamma mu d mu, I gamma mu d mu minus mc over h bar psi. Then there is an action for electromagnetic field, minus 1 over 4 f mu. And then the interaction term is minus g integral d for x psi bar gamma mu psi multiplied with a mu. This is how the SQED looks upon making this rescaling. And here, what I have done, I introduced the coupling constant G has been given by E divided by square root of h bar c. So in this way, this coupling constant G becomes dimensionless. So G is dimensionless. So E has dimension of electric charge, but we know that this combination square root of h bar c also has dimension of electric charge. So where we divide these two, then we get G, which is dimensionless quantity. And in fact, it is related also to what is called fine structure constant. So in electrodynamics, the fine structure constant is defined as, so it's denoted by letter alpha, and it is a square of E squared divided by h bar c, so square of electric charge made dimensionless by dividing by h bar c, and then it's multiplied by 4 pi. No, 4 pi, it's a convention, it's not so important. This you can write as a square of a dimensionless quantity g squared divided by 4 pi. And if you compute this quantity for electrons, then you find out that this is the famous structure constant 1 divided by 137, 0.36. It's a small number, and this is a number which is a coupling constant on which the perturbation theory is based on. yeah, if you want to compute it, this number comes out in the computation in C units. So if you substitute electric charge in coulombs, measured in coulombs, if you restore the constant epsilon 0 in C units, then the result of this computation, if you put the numbers right, then you will get 137.0.36. Find structure constant. Now, all what we know now about the scattering matrix allows us immediately to write down the S matrix of quantum electrodynamics. That's because we know that the interaction potential, we read it from here. So this is a term which describes interaction. And from interaction, from the action, we read of the potential. So potential of interacting theory is h bar c e divided by square root of h bar c, integral, three-dimensional integral dx psi bar gamma mu psi a mu. And if you now substitute this into the formula for the S matrix, then we get S matrix of quantum electrodynamics as being the time moderate exponential of minus Ig. G is just coupling constant I have introduced. The four-dimensional integral of psi bar gamma mu psi a mu. And it is convenient to consider this interaction term. The term describes interaction to be normal ordered in quantum theory. I want to consider this as a normal ordered operator, psi bar gamma mu psi a mu. This is how S matrix of quantum electrodynamics looks like. So the whole information about the processes in quantum electrodynamics, which can be observed in experiments, sit, the whole scattering theory of electrons and photons sit in this formula. That's all what makes the starting point of computation of actual amplitudes, transition amplitudes in quantum electrodynamics. Now, evolution here of the fields psi and a mu is free. We know that these fields evolve in the Dirac picture, in the interaction picture, and in the interaction picture, these fields evolve as free fields. Interaction is non-trivial. Interaction, you see, it's quadratic in psi and linear in a mu. But these fields which constitute this interaction, they evolve as free fields. They evolve as free fields. Now, what remains is to write down this free field expansion or expansion of free fields in terms of creation and annihilation operators. We know these expansions very well. We have already discussed them several times at various contexts. For instance, for fermion psi on x, we have the following expansion. So dk divided by 2 pi sigma 2 square root in full glory with all the factors. This is energy of k or omega on k, depending on how you would like to write it. And then there is a sum over polarizations. You have BR on k multiplied by spinor UR, depending on k, exponential minus ikx, plus d dagger R on k, VR on k. So this is our spinors, U on R and V on R. These are spinors, which provide an independent basis for solutions of the Dirac equation. And you have analogous expression for psi bar. Which looks very similar. where here instead of BR, you have BR dega on K, U bar R on K, exponential IKX plus DR on K, V bar R on K, exponential minus IKX, where BR annihilates electron, so BR and BR dega, BR, VR dega, so this is operators of annihilation and creation of electrons, so this is for electron. And correspondingly DR and DR dega, these are annihilation and creation operators for the positron. And this is how psi and psi bar are written down via this creation annihilation operators of electrons and positrons. We also know that these operators, they satisfy the Fermi statistics, and therefore they are quantized with the help of anticommutators. So anticommutator of BKR with B dega S on K, the same as the anticommutator of DRK with DS dega on K prime, is delta RS, delta function K minus K prime. For electromagnetic field, we have also established in the covariant quantization approach, we have established its expansion formula, so how it expands over the oscillators, over the creation annihilation operators. So A mu on X is with some prefactors given by the following Fourier integral, like this. And then there are these polarization vectors, which in general are time dependent, as we discussed, and they depend on the creation annihilation operators. Remember our discussion of covariant quantization approach. Exponential IKX, where this U and U dega, they are given by certain formulas via canonical field bind. So I will write expression for your reference here. Just remind that this is delta nu mu plus 1 minus lambda 4 lambda k nu k0 squared 2 eta mu 0 k0 minus k mu plus I k mu k nu divided by k0, lambda minus 1, lambda plus 1, x0 multiplied by canonical field bind, I denote it by epsilon, and nu r, and then annihilation operator r, depending on k. An analogous expression is for u mu dega, which would then create creation, which would then contain creation operator. And I remind that here is lambda is a gauge fixing term in the Stuckelberg action. That's the same lambda which stands in the Stuckelberg action. And actually, we know that these terms which are proportional to lambda, which contain lambda, they actually should decouple from the physical processes for the actual physical processes. So they are not that important. The creation annihilation operators satisfy the boson statistics, and for them, therefore, we have AR on K, AS on dega on K. Commutator is minus eta RS delta K minus K prime. The terms here, which are proportional to K nu multiplied with this polarization vector in here as well, they create longitudinal photons, longitudinal and time-like photons only, and therefore for scattering amplitudes with external states made of transverse photons only, these terms are not important. These terms do not contribute. They just disappear if you don't have longitudinal time like photons in the external states. And then this formula, this expansion for A mu, which we can use for computation of such processes involving only transitions between transverse photons, then this becomes very simple. This becomes very simple. So polarization vector epsilon R mu on K, annihilation operator depending on K, exponential minus IKX plus epsilon mu R on K, AR dega on K, exponential IKX. These are all ingredients we have to take into account. So expansions for psi bar for A mu, because this what makes this interacting term in the scattering matrix. And another point concerns propagators. So that's because when we will be computing the S matrix, you know, what we need to do is to expand this t-ordered exponential into Taylor series and then apply Wick's theorem. Wick's theorem, which will bring the time-ordered product of these potentials to the normal ordered form. And we know that this is done with the help of the so-called contractions, which are essentially the Feynman propagators. So we need the Feynman propagators for fermions for practical evaluation of this S matrix. So we need the Feynman propagator between the components of fermionic fields, Dirac fields. And so this contraction is a Feynman propagator, which we have already discussed, I think, in the very first lecture. So Sij x minus y. We can have a propagator between psi bar, component of psi bar, and psi j on y. This is given by minus Sji y minus x. And we also have a propagator between the components psi on x, psi on y. This is actually 0. So if you take just two fermions, then the pairing of them is 0. And the same is for psi bar x, psi j on y and bar, and the pairing between this is 0. So when you will be computing the pairings and Wick's theorem, then you need to take just pairings between psi and psi bar. Where this quantity Sij, x minus y, is I integral d for k 2 pi in the power 4 gamma mu k mu plus mc over h bar element. This is a matrix, and I'm taking this matrix element Sij. This is a matrix because here you have Dirac matrices, and in the denominator you have characteristic expression involving I epsilon, and then you Fourier transform it to get the propagator in the X space. This is how it looks like in the Fourier. Looks like as a four-dimensional integral. Now we also have a propagator for the gauge field, A mu on x, A nu on y. We have discussed it. In full generality, with the parameter lambda, it looks as follows. So minus I exponential minus ik x minus y divided by k squared plus I epsilon. So mass term is epsilon because we are talking about photons. Here you have eta mu minus lambda minus 1 divided by lambda, k mu k nu divided by k squared plus I epsilon. And we have discussed that we can use various gauges by fixing lambda. For instance, we can use the Feynman gauge, where lambda is equal to 1, and then this term with k mu k nu absent, so you get just propagator proportional to eta mu. Or you can use Landau gauge, where lambda is sent to infinity. Now, for practical computations, it is very convenient to represent the scattering process in terms of visual diagrams, which allow you to get a certain intuition on the matrix elements of scattering matrix. And for this reason, one usually introduces a geometric notation for various objects, various blocks or building blocks of scattering theory, which are called Feynman diagrams. Feynman diagrams. So the Feynman diagram for the photon propagator is usually denoted by the wave line, like this, and it's a graphical representation of what you call the Feynman propagator. So this is a graphical representation where, say, your photon has been created at point X and disappeared or been annihilated at the point Y. And this is a notation for a photon propagator. Photon propagator. That's one building block, which we will meet when we will be computing the matrix elements of the S matrix. Another is a fermion propagator, so from X to Y or from Y to X, and it has arrow in it depending on what is standing first, psi on psi bar. So this is written for psi and psi bar propagator, like this. IJ, then this is fermion propagator. Propagator. And there is another ingredient which describes an interaction term of the S matrix. It describes a photon getting into the vertex, and out of which you get two arrows. One is getting in, another getting out. And this vertex signifies an expression of the type minus IG gamma mu. That's exactly this insertion minus I gamma mu, which you have in the S matrix. Minus IJ gamma mu. That is an expression which you will get in the S matrix. A mu is a electronic, is a photonic wave line which gets into the vertex, and this two psi and psi bar are described by the lines with incoming and outgoing electrons, like this. So this stands for the diagram describing the interaction vertex. And I think already in the next lecture, I will show you how to visualize the orders of perturbation theory of S matrix. They come to us actually as time moderate products of integrals describing these interaction terms, but we can actually visualize the evaluation of these matrix elements in terms of these Feynman diagrams, in terms of these Feynman graphs, which makes maybe the practical computation of this S matrix easier, because at the end of the day, you don't even need to write down these integrals and make their computation from the very beginning, but you can use as building blocks these Feynman graphs to write down directly the last formula, which for the integral which you need to compute to define the corresponding scattering amplitude all the contributions, the relevant contribution for the scattering process you are interested in. Okay, so this is what we will do next time. Let's take back this formula. And what remains to be also defined before we come to the actual example of computation of the scattering amplitude is to define the scattering states. So we need a state in the asymptotic Fock space, say containing n photons. So number n pH will denote the number of certain number of photons. Then external states might contain a certain number of electrons. And finally, you can also have a certain number of positrons, and P would be the number of positrons. And then the external state, an external state which contain, say, photons with the momenta K1, K, and photon like this, then certain number of electrons with momenta P1 and so on, P an electron, and then a certain number of positrons with momenta Q1 and so on, and P positrons. These are states in the Fock space, and they are defined in a standard way by applying to the unique vacuum state the corresponding creation and annihilation operators. And if you want this state to be relativistic covariant, then we need to introduce the corresponding relativistic prefactors for photons, for electrons, like this. This is for electrons, and then for positrons, like this. Q positrons, Q for positrons, cross, and then the corresponding creation operators. So creation operators for photons, creation operators for electrons, and the creation operators for positrons, which are these: d dagger on Q1 and so on, d dagger on Q and positron, and then all acts on the vacuum. This is our generic external states in the Fock space: certain number of electrons, certain number of positrons, and a certain number of photons. And then what we need to compute, if we want to compute the matrix elements and eventually the scattering amplitudes in quantum electrodynamics, then we should take our this matrix of QED and sandwich it between final and initial states, each containing a certain number of these asymptotic particles. So at the end of the day, this will amount to the computation to the computation of normal ordered expressions sandwiched in between these asymptotic states. So very similar to what we have already done for the case of the complex scalar field. So my idea on the next lecture to show you quickly the computation along these lines of the Compton effect or Compton scattering, where photons scatter on electrons. And classically, this is a scattering of light by an electric charge. In classical theory, it's called Thomson scattering. Thomson scattering, then this is a scattering when just electromagnetic wave falls on a charge. Charge start to oscillate under the influence of the incoming electromagnetic wave, and the oscillating charge moves with acceleration, and the accelerated charge radiates. So there will be outgoing radiation. And in quantum theory, this is nothing else as a Compton effect, which you can consider as a scattering of a photon by an electron. And that is what I would like to compute for you in the next lecture, to show you a very explicit computation in quantum electrodynamics by using all these quantities and all these pieces of the theories that we have introduced. Okay, I think for today, that is all what I wanted to tell you. Thank you.
Thank you, sir.
Thank you, sir. Also, could you please send us your notes? Because last semester you sent us your note, but only the first 4 chapters. Can you send us the rest part?
Yes, yes, I can do that.
Thank you very much.
So in my lecture notes, I consider a bit more. I consider several effects in electrodynamics. What I consider is the Müller scattering of electrons. So 2 electrons get in, 2 electrons get out. So scattering of electrons, and there is a Compton effect. And finally, I also consider the annihilation, of an pair annihilation. So when you have electron and a positron annihilated into 2 photons. These are all effects 2 to 2, and they are all effects very important in quantum electrodynamics. And for all these effects, I compute explicitly the corresponding scattering amplitudes. We will do Compton effect, but you can also look how this is done. And for other processes, it's done in a very similar way.